explanation methods in general. So first application which we did is to compare different models. So I will show you what I mean. So for example, on the text domain, we trained 2 different models to classify this 20 newsgroups data set. One model was based on word-to-vec representation and a CNN architecture. It got 80% accuracy on this data set. Another model was based on more classical features like back of words features, so it counted the occurrence of different words in the vocabulary, and we used a support vector machine for classification. So like the upper model is what people are using more or less today. The lower part is what has been used a couple of years before. So as you see, like both models reach almost the same accuracy on this data set. So on this data set, like deep nets are not outperforming. This was also observed in other work, and it has mainly to do with the simplicity of the data set and the simplicity of the task. But if you get the heat maps and you analyze the strategy which like each of these methods learns, you see a huge difference. So in terms of errors, both methods are more or less the same, but in terms of strategies, the word-to-vec model, of course, like identifies semantically important words and focuses on these words to classify the text, to classify the document as a specific topic. For example, in this case, this is like a text about medicine. And it identifies words like discomfort, body, sickness, and so on to classify this text according to this category. In the back of words model does equally good in terms of performance, but it doesn't have access to the semantic representation. It doesn't have access to this word-to-vec representation, so it mainly relies on statistics. It classifies the text according to statistics, how often several words occur in this text, but in terms of performance, both of them are equally good. But for us, for humans, I think most of you would agree that the upper model is better because it gives like really intuitive explanations how it comes to its conclusion, whereas the model below is more, it's much harder to interpret and to understand what it does. Also here we see for these 2 models we see the most relevant words in the test set. So we see for the class medicine, we see that this CNN model, word-to-vec model, identifies words like symptoms or treatments as very relevant. It even identifies words which have not been in the training set. So the words which are underlined have not been in the training set, but are still identified as very related, very relevant for this task. The back-of-word model cannot do this because it relies on the vocabulary which has been computed on the training set, so it cannot identify these words. And the words which are marked in these red boxes, they don't seem to be, for us at least, they don't seem to be really semantically related to the category medicine. And still these words are assigned high relevance by the back-of-words SVM models. You see from this slide that it makes really a difference, even though it doesn't make a difference in terms of performance. It makes a difference in terms of which model uses semantics and has a better idea of what's in the text. First example. Then the second example, we did the same thing for classifiers in the computer vision domain, of course. So we compared here two models, like the reference model with 8 layers on ImageNet, and a GoogleNet with much more layers and much better performance. And also here we see, if you look, I don't know if it's visible, probably yes, that both models like have a different focus. So the Google Net really focuses on the faces of the animals. It's much sparser than the reference coffee model. It's much sparser, and it's kind of better suppresses this background noise. It doesn't put a lot of relevance in the background, but really focuses on the object itself, on the face, on the details which are important for classification. So the theme, we don't fully understand it yet, but there seems to be a relation between the architecture, the structure of the model, the number of layers, the type of layers, and so on, the performance it gets, because here we see obviously that Google Net is better. It has a different structure than the Coffee Net, and also the heat map. So I think in future work we should study these relations to better understand how like the structure and performance affect these explanations, because in the end we want to improve both. We want to improve on the performance, but we also want to get some meaningful explanations, and of course relevant question is how it depends on the architecture, how it depends on the structure. Can we come up with architectures with structures which kind of improve both? So this is just like a question mark for you guys to figure it out. Second application. So we saw that we can compare different models, but we can also quantitatively compare them. What do I mean by this? Like, we can quantify the use of context with LRP. I mean, if you have a bounding box, like for example in this Pascal VOC images, you have bounding boxes around the objects. So it's like natural to measure how much the model uses context, because you can measure how much relevance falls outside the bounding box, how much relevance falls inside the bounding box. So if this gives you like the importance of context. If a lot of relevance falls outside the bounding box, then context is really, really important for the model. And I think it was always the question like that, people hypothesize that for some classes like airplanes, maybe context is not so important, whereas for other categories, context could be more important because it's much harder to identify the object itself. So, but we can quantify it. We can, with the relevances, we can see how much context information is used. And the nice thing about LRP is that it decomposes the classification, the decision. So it allows to meaningfully pool over this bounding box. So you can just, instead of computing like instead of summing the relevances over the whole image, you can also like sum it over the bounding box and see how much relevance falls inside the bounding box, how much falls outside. And we did that for the Pascal VOC data, for the CoffeeNet model, after some fine tuning. And we see like larger values means that context is important. So here we see that, for example, for airplane, context is not so important. Like the model really focuses on the object itself. And for class like sofa or chair, for some indoor scenes where the images are much less structured and less clear, the model like focuses also heavily on the context. So there seems to be like a difference between different categories on how much context is used. And what we also did is we made it the analysis. We extended this analysis and compared different architectures. So here we have three architectures: VGG, GoogleNet, CoffeeNet. We divided, it's on ImageNet data, so we divided the classes into three categories. So the first 333 top classes, so the classes which are well predicted. Then this is always this right thing. Then we have like this middle class, so where the performance is like in the middle, 333 classes in the middle, and the 333 classes which perform very poorly. And you see, like on the y-axis there is context use, and you see that the performance is anti-correlated with the context use, which means that if the model is focusing is putting a lot of relevance in the context, it usually gets worse performance for this class. And also, like if you compare it across the models, you see that this Cafe reference model has like the worst performance among these three architectures, and also like it uses much more context, at least for the classes which are with bad performance. For the left yellow part, you see that like there is much more context used. So in some sense, the model was not able to identify the class and really put the relevance on the class. So it puts a lot of relevances in the context, and this leads to a bad performance. So in some sense, like focusing on the face of the animal is a good strategy and shows that the model performs well. If the model puts a lot of relevance to the context, it's kind of it's unsure, or it shows that the model is not very certain with these predictions. Third applications. So of course, what we also did, we compared not only models, but we also compared different configurations of models. So we have one model, and we do like pre-training, no pre-training, and like different configurations for one model for different models. So we did this, for example, for the face analysis for the age and gender prediction on this audience data set with 26,000 images. We got near to state-of-the-art performance on this data set. Had a presentation at last year ICCV workshop, but here you see that we compared different model configurations. So, for example, we see that the performance for age classification is best with when we mix the aligned images with non-aligned images, and when we use when we initialize the model on EMDB wiki dataset, and also use the VGGNet. So this model reaches like 62.8%, which is like very good for this age classification task. If you use, for example, another type of initialization, if we initialize on ImageNet, then the performance is less. In this case, 56.5, and so on. So we can compare like different, we have different values for different configurations for this age and gender prediction. And what we also did is we wanted to understand, using heat maps, what did the models really learn to classify men and women, or to classify age. And here is one example. So here you see gender classification, and we see a model which uses pre-training. This is a heat map in the middle, and the one without pre-training. And you clearly see that the model which uses pre-training focuses on the chin or the beard when classifying men as men, and focuses on the eyes and hairs when classifying women. Whereas the model without pre-training, the heat maps are much harder to interpret. So it seems to overfit on the data a bit. It seems to not really finding the intuitive way of analyzing faces. So pre-training can be seen like as a very important step for this task, not only in terms of performance, but also in terms of how semantically meaningful these explanations are. Because, I mean, it makes sense that the model looks at the beard or the chin for men and at the hair, for example, for women. Here is another example which is quite nice. So for age classification, here we used a pre-trained model on ImageNet. It got really good results, and it correctly classifies these images, these two ladies. So the first one as belonging to the age category 25 to 32, and the other lady as 60 plus. In both cases it was correct, but if you analyze the heat map, you see that for the first woman, laughing is important for this classification. So laughing supports this classification, that she's young, she belongs to the category 25 to 32, whereas for this older woman, laughing speaks against this classification. In other words, so the model learns that old people don't laugh, because if old people laugh, then it speaks against being old in some sense, and which is a clear bias in the data set. this clear bias in the data set, and you won't be able to recognize it if you don't have those heat maps, if you don't have access to this information, what these models really learned. And the cool thing is, if you use another pre-training, if you pre-train on faces, then this bias disappears. So like in this case, also like the way how you pre-train, how you do this training is important, not only for the performance, but also like on how which features are finally used for classification. Another example is where we applied these techniques to face morphing attacks. So here the idea is that you have two real faces, and you create a fake face. And there is this attack, and if you have, like, for example, this fake, if in the ID, like this fake face is in your ID document, then both real persons could go with the same ID and wouldn't be recognized. So it's like an attack on this face morphing. And it's, if you look at it, it's not, I mean, it looks as a real face, so it's quite hard to detect for us humans. And what we did is we trained different models, or we compared different ways of training. So in the first case, we just trained a model on morphed faces, so fake faces, and faces which are real. Okay? This is the naive one. Then we also trained faces of 50% of real faces, genuine images, 10% of faces which are completely morphed, and 10% of faces where we only morph one region of the face. So here we morph 4 regions. So we morph the left eye, the right eye, the nose, and the mouth. So these are the 4 regions which are morphed in this case. So we could, so this one morph example, like it's a different, so you train on different data in some sense, but you in the end we want to solve the same task. Then you can also define more complex morphs where you have 50% of real faces and 10% of complete morphs and 10% of partial morphs, where you, for example, morph the eyes and the mouth, or just the left eye and the right eye, or you have all this different combination of morphs, which you use as training data. So you have more complex morphs. But also here the task is also like the same. You want to classify morphs. And the multi-class example is here we have like a more complex network where we have like we don't have a binary classifier. We have like output for the eyes, for the mouth, and so on. And after that we retrain it by just retraining the last 2 layers to have a binary classifier. And you see in terms of performance, they are more or less the same. This multi-class network works slightly better than the other ones. But there are not so much difference. So on the tests, so we evaluated it on test data, which is just like complete morphs and complete real images. And then we try to use 2 different attacks on this data. So we kind of, one is a semantic attack where we tested the robustness of these models on partial morphs. So where we just morphed the left eye or the right eye or the nose or the mouth. And we see that, for example, the naive model, which was trained on just the real images versus complete morphs, doesn't perform very well. So it's not able to recognize these partial morphs as morphs. Whereas the other ones, the performance drop is minimal. Also, like when it comes to adversarial attacks on this model, black box attacks, there is a difference in how they react to these attacks. So, I mean, this analysis just shows you that the way you train your model has an impact on this robustness of the model, but not only on the robustness, but also on which features the models use, and which means also on the heat maps which we get. Yeah, so what keeps this? So we computed like this heat maps for these different models. Where we, for example, in the first row, you see the naive model, which was trained on left versus on true of full morphs versus true images. And what we did is we just changed the left eye, and we see that the heat map like focuses on the part which are changed. which is good. But for example, for the nose and mouth, the model is not so sure, like it doesn't identify like the parts which have been changed. Whereas with a model which is a one morph model, which also like uses one morphs in training, has much more meaningful heat maps. And the interesting thing is that this multi-class training, the model which uses this multi-class training, the heat maps seem to compare different structures. So even, for example, we just morphed the left eye, we didn't get a response on the left eye. But the model seems to identify the original parts. And for example, in the third row, you see that on the left that we morphed the left eye, but there is no response on the left eye. There is just response on the mouth and the nose and the right eye. So this model kind of compares different parts and checks if they are original, if they are like real. But the left eye is morphed, and the model like recognizes it. But it's for us it was harder to interpret these heat maps. So also this example shows you that different training ways you train your method may lead to different strategies. So sometimes the model doesn't identify the parts which were changed, but it's just comparing parts. And so the heat map shows you that it compares like different parts, and therefore like it assigns relevance to the right eye and to the nose and to the mouth, but not to the part which were changed, the left eye. So also here, the heat map gives you some kind of insight how this model works, but sometimes this insight is unexpected. I mean, in this way, we didn't expect that the model like performs like that. Anyway. Yes, so another application on text, what we did is we used this heat relevances to learn new representations. What do I mean by this? In this word-to-vec example, you have a text, for example, some astronauts occasionally do something, and for every word you have a vector, you represent as a vector, and if you classify it, if you have a classifier, you get also like a relevance for every word, or even you get a relevance for every component of this word-to-vec vector. And what we did is, okay, we thought, why not like having like averaging, doing a weighted average of the relevances which we get and the words in the document. So we classified the document, got a prediction, then got the explanations, got the relevance value for every word, and then computed the document vector, which is the weighted average of the relevances and the words. And the nice thing is that if you do this, and so you have a document vector for every document, so you have one vector for every document in your data set, and if you then compute a PCA on these document vectors, you will get a really structured documents. So you can see it here, like every color is a different category of the word-to-vec on this data set, on this 20 newsgroup data set. So even though the whole process, I mean, if you have the classifier is unsupervised, so you just apply PCA to these document vectors, you get a nice structured information. If you just uniformly average these words without this weighting, you will not get the structure. So you have like a very uniform blob where everything is combined, but you don't have like this nice structure. Also, if you apply some TF-IDF weighting, you don't get the structure. But if you have a classifier, if you have like these explanations, this example shows you that you can arrive at new representations of your document. So this is just one example which we did in this paper, but I think there is a lot of other possibilities of how to extend it to get new representations of your data with information from the explanations. So here you have these relevances, and you use this to get a new representation of your data. Another example. Understand your model and get new insights. This is, I think, which all of us want. So I have a few examples on that. So first, we start with this Fisher vector classifiers. So I told you that we extended LRP also like to this Fisher vector SVM framework. So I won't go into detail on how you redistribute, but the concept is the same, that you want to decompose the function in terms of relevances. And you have this relevance conservation property. And yeah, so we did this for this Fisher vector pipeline. And for example, classified images on Pascal VOC 2007. And you see that if you, for example, classify this image with the bike and you explain the bike, you see that the model really focuses on the bike. If you explain the person, the model focuses really on the person, which is as expected. But for other classes like the boats, you see that the relevance is not really on the boat, but on the water. So also like on the trains, on the left train, the model really focuses on the train, but on the right train, it focuses more on the tracks. So this example also shows you that these models are not perfect, and sometimes you don't get what you think you get. Or these models don't learn what you think they should learn. And these things happen all the time. Another example with this Fisher vector classifier, so what we did is we used this code from Kantorov and Laptev, which was presented on CVPR a couple of years ago. The idea was that we want to do action recognition on the HMDB dataset, but not on the in pixel space, but on motion vectors. So this is very efficient because usually videos are compressed, and you can extract these motion vectors without decompressing the whole video. And Kantorov and Laptev showed that you can get good results on this data set for action recognition, and you are very efficient. And here is what you get from the heat maps. Is it work? Yeah. Here is what you get from the heat map, is that, for example, for the action chew, so you see that this is the action chew, the model doesn't really focus on the chewing part of the face, but it identifies the movement of the head as like distinctive for this class chew. So also here, like this movement pattern, which is relevant, is not related in a strict sense to the action. And so, I mean, these things happen all the time with these models, and if you don't understand what they are doing, you may think that these models are really like focusing on the chewing, but actually they are not. Another example where we try to understand the model here, again on text. So on the sentiment classification task, we use this LSTM model. So I mean, one thing which was kind of new in this paper, which we did, is that these LSTMs have this multiplicative interaction. So it was unclear at first how to redistribute relevance over this multiplicative gate. So we came up with a rule, and which works quite well. I want to go into details on that. But the nice thing you see at the examples below. So when you predict negative, so all these sentences have negative sentiment. So you see, for example, too slow, too boring, and occasionally annoying. So it was movie rating, and you see that like annoying is very relevant for this negative rating, which makes sense. But also like words like it's neither as romantic nor as thrilling as it should be. So here like this negation gets a high relevance, because romantic is a positive word. But because if it's negated in this case, it gets a negative meaning. So the model like really understands negation, or learns. We can verify that the model like understood this, that in this context this word has a negative meaning, which is quite nice and quite cool. Another example on videos, we applied our LRP approach to video classification on the sports 1M million data set on the C3D model. And we wanted to explain the videos. So we get here, you see some explanations over the frames. Here you see like how it looks if you play it. And on this model, we get a nice insight. We got the insight that here you see the relevance distribution over frames, and you see that the model like really focuses on the beginning of the frame and the end on the frame. So there was more relevance on the beginning and the end of the frame when you consider the 16 frames series than in the middle. So it seems that the model like tries to watch more of the movie. It focuses more on the outer parts of the video, and not it doesn't uniformly redistribute the relevance. And based on this, we came to the idea: okay, why not play this video and fast forward? So give the model more of the video. And this is what we did, and we got a quite nice result, because we got, without retraining the model, we got an improvement in accuracy just by fast forwarding the video. So you see, for example, the red part, on the x-axis, you see the accuracy and what we did. I mean, you see how many frames it used, and if we move from the left to the right, the model like saw more of the video, so it captures more of the frames, and you see that the accuracy also increased in this case. So it's kind of for free. It increased for free. What we also did is we applied it to speech, to audio data set, and for example classified male and female speakers, and got the result that the model focuses on. So here the model was trained on spectrograms, and we saw that the basis, the fundamental frequency and the spacing between the frequencies, the harmonics, are very important for distinguishing men and women. And this has been also like described in the literature a couple of times before. So like this is a fundamental feature which distinguishes men and women speech, and the model like correctly uses this information here without us telling it to do so. Also, like here, a verification that it works well on this VQA task on the clever data set. We see, if you ask the question, where is the metallic cube? Are there any large cyan metallic objects behind it? So like words like behind is very important. And also you see in the image that the model focuses on the right part. And on the right you see like different question types and relevances for the most important words. So you see that if the question regards like the size, equal size, then size becomes a very relevant word. If the question has something to do with counting, then words like how or how many are very relevant, and so on. So we can verify in this case that the model does something useful, and it learned the semantics behind these questions. So one of our favorite LRP applications is this one, where we kind of play these Atari games and see that we get relevance. I mean, on the right side you see like the LRP relevance. On the left side you see when you use sensitivity. You see that LRP really focuses on where the ball is, whereas sensitivity focuses where it could be in the next frame, not where it is. But by looking at these videos, I will show you that you can also learn something about the model. You can learn something about the model in the sense that, for example, you can look at it where you can compare different models after different training iterations. So you can compare like the model which after 0 epochs, so after the initial model, you can apply it. You see that the model puts relevance everywhere, but it's quite static. It doesn't track the ball. Maybe I should mention that in this case, so the game was fixed. So we recorded the game using a model which can really play this breakout, and we then applied different models, like the 0 epochs, the 25 epochs, and the 195 epochs model to get the explanations. And you see that the model which like plays very well, like focuses on this tunnel, and it focuses on the ball, and it really gets the meaning of the game, whereas the other models like at first need to track the ball and get sense of the game. So of course we didn't only do it for this Atari game, but also like for others. where you see like this pinball. We also got some nice insights that maybe if you have played pinball yourself, then you know that you can, but you can, there is one way of playing pinball is not to controlling this these taps, but you can shake a bit with the table. So if you move the table a bit, this is called nudging. You can also like play, if you're a good player, you can try to trick the system. And in this case, the model actually really learned to apply this nudging strategy to play pinball, which was unexpected before we analyzed it. And yeah, I mean, you can, here is like the summary of this one plot. You see when you track this relevances, we measured relevance on the ball, on the pedal, and also on this tunnel areas. And we saw that, for example, at first the model learns to track the ball. This is the first thing the model does. Then it learns to track the pedal, which controls the ball. And only later, after that, it tries to focus on the tunnel. So you can kind of make sense of the strategy of the model by tracking its behavior and by looking at these explanations. Yeah, that's basically it. So you can find like some code tutorial software and in our homepage, and there is like a tutorial paper which I recommend if you're interested in this topic. And there is this new toolbox which we have, and all the references which were mentioned by me in this talk will also be available on the slides. So our slides will also be available online, so you can check it after the tutorial. So now, thank you very much. Are there any questions regarding these applications? So maybe you can set it up, and if there are any questions. Yes.
It seems like all your examples were based on classification. Is there anything that can be done with regression type tasks?
I will come to an example like that.
Great, thank you.
Yes. Okay, so thank you very much.
All right. So, try to set up things. Okay. So, the last half time. After we've seen, a course, intuitive introduction, serious math, and proofs, and a lot of very impressive applications that are in computer vision, gaming, and many contexts, I will change gears a bit and talk again a bit more general, and then I will use explanation to actually gain some insights in the sciences. So we will first have a bit of neuroscience, then we will briefly talk about quantum physics. I know it's quite a stretch, but it's going to be fun, and then some medical image analysis where the regression was an issue. And then I will wrap up. Okay, so let me just show some more almost philosophical issues, but I think they are important. So right now, what is actually being done in machine learning or in computer vision is that you use the standard model of machine learning. Namely, you have your data, you train your model, you do your cross-validation, you're not looking at the test set, and then you report on some hopefully excellent results on the test set. Okay? And so I'm just asking the question, is that actually all what we need? And I would like to share a nice example that we had in CVPR 2 years ago. So this is like the standard approach that people would be doing, the standard exercise. You take some benchmark data set you train your model, and you make it perform really well, and then you write a paper and report superior performance. And for example, in this case, we took two models. One was just the deep network. It was not even our deep network. I think this was AlexNet or something. The data set, by the way, is a slightly old one, which is VOC 2007, I believe. And also we trained a Fisher model. So both of them are pretty good. Sometimes the deep net was better, like in the airplane. And Wojciech was actually talking about this here. So Fisher is using too much of the context here. Same with boat. And then there's some innocently looking class, which is the horse class. And if you look at this, the generalization error rates of both models, they don't differ much. I mean, this is not statistically significant. So in this case, you've done the best, your models are almost comparable. This is what the generalization error says. And now we're looking at explanations of what these models do. And I'm showing this to you now. Okay, so here's the horse class. So obviously you have some horses. And this is what the deep neural network does. It looks at the horse's nose. It looks at the rider. It looks at the horse's butt. Okay? And all of this makes a lot of sense. So the generalization error is well deserved. So you're looking at the object. Now look at the Fisher vector model that is very good out of sample, comparable to the deep neural net. And basically you see that the model looks mainly at the context, also a bit on the horse's butt again, so this seems to be characteristic. But most importantly, it looks at the lower left corner, and you wonder why. Okay? So I will read to you what is in the lower left corner, and it says Lothar Lenz Pferdefotoarchiv.de, which is a tag which just so happens to be in the horse class. So think about it. So this model has learned the concept of a horse, and this model has learned to cheat, which I think is perfectly fine. It's both very intelligent behavior, by the way, because we are now talking about AI and everything. But practically in the lower left corner, there is just the tag. And think about it. This is a data set that we as a community have been writing on quite a bit. So it's quite interesting. These data sets are now millions of data points, and I would make a bet that they contain artifacts like this one. And if you think about it now, from what I asked, so the generalization error actually tells us that both models are equivalent. But the way they are solving the problem couldn't be more different. One is looking at the object, that's a deep network in this case, and one is cheating, or looking at an artifact. So if we want to use these models out in the wild doing computer vision, in a self-driving car, in medical diagnostics, which model would we like to have? We would like to have a model that is actually doing the things such that we are able to really broadly generalize this. So these artifacts are happening in benchmarks, and we're looking at benchmarks. And so I think that it's of course, these artifacts and this behavior is also a reason why we have, it's a reason for the limitness of the benchmarks. If we would have infinitely many data points, talking as a theorist, of course this wouldn't happen, right? Or perhaps less. But we don't have infinitely many data points, and we have data from different distributions containing artifacts and all that. So I think it's absolutely mandatory to understand your model if you apply it in the wild. So having said this, if you are very good in predicting something, there are still some applications where you can make money, whether you use artifacts or not. But if you use these models in the sciences or in medicine, it's going to be a disaster, because a lot of people are now using models that we have created, and there's a lot of nonsense going on. So we need to understand our models. So, and now I'm telling you a bit about some of the scientific things that we have been working with, and you just sit back, relax, and enjoy. It's not going to be computer vision for a while, but maybe it's still fun. So, neuroscience. So, there's something that is called brain-computer interfacing. And in brain-computer interfacing, we're measuring data from the brain, and we're trying to decode brain states in real time in order to control things, like computer games, wheelchairs, whatever. And so there's a lengthy procedure how to get features from that, how to get rid of artifacts, how to use models. But this lengthy procedural thing, we can start to see what is actually going on in the decoder model. And so we can try to see whether the decoding model is actually doing the right thing in terms of neuroscience. So I'm just to make this a bit more interesting. So about 20 years ago, we started working in this field, and it was a small field, maybe 12 groups in the world, mainly medical groups. So they used electroencephalography, and they had patients that are locked-in patients, and their motivation was to reinstate the ability to communicate again. And they did this basically by training the patients, the locked-in patients, by biofeedback, so that they would change their brain signals such that they could be decoded with the simple signal processing that was available then. Then I suggested to use machine learning in this context, and we went basically from something like 3 hours of training on the patient side, which was the state of the art then, to something like less than 5 minutes. So, which means that you can come to the lab, get geared up, then you do your little feedback training, and after 5 minutes, you're ready to go, more or less. So, and I would, of course, show a video to this if it works. Hopefully it does. But I'm showing you a subject here. The subject is wearing an EEG cap. It's 64 channels, 1000 hertz, and this is going into an amplifier that is, each 32 channels is as expensive as a small car. Then this goes into a laptop, and then the laptop does an online decoding, and the subject is me. I'm trying to play this game of brain pong. So I'm controlling this paddle in real time in order to hit the ball as often as possible. So first of all, it's very important to know what kind of brain states is being decoded. So you will not see me move, but you can ask, what did I think about? And one thing that I thought about was, I imagined movement of my right and my left hand. So imagination of my right hand has some motor cortex signal change on the left hemisphere, left hand on the right hemisphere. So having, so to say, filtering this out actually allows you to get 1 bit out, which is enough to actually get going. So, and I'm focusing the wall above the screen, so I'm not focusing the ball. So this is already some time ago. You can see the NIPS 2003 poster. So after that, so this was maybe 20 years ago, 15 years ago, something like that. Yes, and from that moment on, because you could apply machine learning, everything was very easy because it could be applied easily not only for patients but also for general neurotechnology. So, and by the way, this is fun. And by the way, you can also play this against each other with your brain, two brains coupled. And also, I'm good at this, so people at some point, members of my lab refused to play. So what are the applications? There's hope for patients that are not only the ALS patients, that locked-in patients that we could hope for help, but also stroke patients. So we can use this technology for applying in the neurosciences and redoing experiments. And we also can use this technique for all sorts of interesting neurotechnology. And I would like to give you the most obscure application that you would probably never think of. In Berlin, there's I have a colleague, his name is Thomas Wiegand. He's the father of H.264 and 65 and 66. And so that's the standard video coding, the video coding standard that we have. And you probably know that in MP3, people have been coding according to our perception. So we thought at some point, why not try this also for video? Why not just, code what we perceive, just that? And then we used a brain computer. I mean, by the way, we put this into a grant proposal, and of course the grant proposal was rejected. Saying with a reviewer saying that this is the most nonsensical thing that they have heard of, but we still did this and wrote some papers. But practically we got some insights on the perception on human perception that then allowed the engineers of the Fraunhofer Institute HHI to actually go about and design some new decoding principle that was actually, I think, 10% better. And 2 years ago, the Champions League final in Berlin was broadcasted by that. And 10% on the global level always corresponds to a bunch of nuclear power plants in terms of energy. So think about it. We start for something completely innocent, and then there we go. But I wanted to come back to the explaining thing, because in the end you need to know whether or not there's some horses in this, right? So whether we are just transmitting because of some artifacts. And here's what the deep neural network explanation is saying. It says basically for the first class, the right imagination class, we have our, our heat map says that's the area. So over the motor cortex, that's the area that is being used for decoding, and for the left class, it's the other way. So you see that even physiologically, this model is actually able to deduce what it should be deducing, because we know how physiology works in this case. So one more thing is there are some more adventurous paradigms, and there's also the possibility to run this in real time and to get a real-time explanation, which is very interesting for the neuroscientist, because so far they've only looked at average interpretations. Okay, so now the stretch becomes a bit more. So we're talking about quantum mechanics now. Just bear with me for a moment. So here's an innocently looking equation, which is an eigenvalue equation. That's the Hamiltonian, that's the wave function, and that's the energy. So that's the so-called Schrödinger equation. It's the governing principle in all quantum mechanical systems. So if we want to know about quantum mechanical properties of molecules, of drugs, of the DNA, of materials, anything, then ideally we would like to solve this equation. But this equation is really hard to solve. It's a pain. So you can't solve it. So, if you would naively write it down, it would be something like a 10 to the 60 dimensional eigenvalue problem. But only if you write it down naively. So people have invented some approximation techniques for that, and they are called DFT, which is not discrete Fourier transform, but density functional theory, which got some Nobel Prizes. And with that, you have an approximation to the Schrödinger equation, and the most used approximation for a small molecule, you have to spend something like 5 hours of computing time per molecule. So in the cheapest approximation. So this is why these people are using supercomputers as much as the climate people. Everybody else is of measure 0, even us. So what I suggested was to say, well, this Schrödinger equation, let's treat it like a black box and try to predict its outcome. So which is heretic in many ways, because you try to predict the outcome out of an equation instead of solving it, and it's also heretic from chemistry and physics perspective. This was during my sabbatical at IPAM at UCLA in 2011. So then, if you do machine learning, you think about data. So there's, by the way, more small molecules than atoms in this universe. So it's a combinatorial explosion there. So someone, Bloom and Raymond, they numbered all the molecules up to 6, 8 nodes and up to so and so many heavy atoms. And we used part of this data for training. So someone practically ran these DFT calculations for about 7,000 molecules times 5 hours on a supercomputer to get us the training set. And so how do we represent this? Well, we represent it in the first approximation. This was our paper, Fizeref letter in 2012. By the way, this was the first time that machine learning was applied in this context. So this was like a game-changing paper. So now, by the way, this community has had last year 10 workshops only in the US on this field. So it's a growing community. So assume that we have this molecule, and we would like to represent it, and we take the Coulomb force between the ith and the jth atom and write it into a matrix. So then we have one molecule represented by one matrix. And then we take the Frobenius norm distance to compare them, and then you put it into a kernel matrix, and then you do a regression. And of course, we all know that this regression can be solved in closed form because it's kernel-rich regression. That was the first thing in 2011, because I insisted that we use the most simple model before we go to something more adventurous. And of course, we went to something more adventurous. At that time, actually, our Fizeref letter said that we can do 10 kcal per mole accuracy. The chemical accuracy, the one that the dream of chemists, is at 1 kcal. So already at the NIPS 2012, we would be able to go to 3.5, then in 2015, 1.3, and we are now at 0.3 kcal. So, and just to remind you, it's not taking 5 hours per computation, but it's taking fractions of a milliseconds for every prediction. So we are at the same accuracy, but 10 million times faster. So now we can do neural nets, because in neural nets we have the possibility to make them deep, and to put all the prior knowledge inside. And this was a paper published in Nature Communications in 2017. So the idea is now, again, we take the distances that we before put into the Coulomb matrix, and then we have for every atom of the molecule, we have this kind of module. And so basically, what we try to do practically is by making the neural network, by designing it in a particular way, we design the interaction that the neural network allows for these molecules, for the atoms and the molecules, to be physical. So in principle, all of you know word2vec, so I don't have to explain for that. But we are trying to do something like word2vec for molecules. So in other words, we're trying to find the local chemical environment embedding in order to actually properly represent things. Kernel-rich regression was using a kernel where we have put our physics knowledge inside. This is now learning the representation from the data that we have. Also, it's a bit more scalable. So we have this tensor layer, and each interaction layer allows to do a refinement. So, and then in the end, we add these things up. So practically what we do is we, in the first, box of this kind of thing, we represent every atom by its local chemical environment. Then we go one step further, so we have the concepts of bonds, and then we have more long-range interactions. So now, because this is a talk about explaining, the prediction quality of this model was outstanding. It's a 0.3 kcal in its latest version, which is the current standard. So the question is now, this model, this deep neural network, has learned to predict super accurate the quantum chemical properties of molecules. So that's nice. So can we actually gain insight from it? And that is something that we have been able to. So now our model is trained, and because we hope that this model is not horsing around and doing artifacts, but it's actually focusing on the right things. And so basically what we can ask, we can basically apply this explanation framework on one side, but also we can apply an adaptation which is physical, which puts test charges across the neural network. So the neural network is able to provide some chemical potentials, local chemical potentials. So this is now for material, so it can be applied to materials. And you see a very nice structure. Materials are, they have a lattice. And this is now for molecules. And you can clearly see, these, maybe it's better on this slide, you can see if you are hydrogen, where would you bind? If you're carbon, where would you bind, and all that. But most importantly, the question is, can we actually get something out of the model that has not been in our database? And the answer is yes, we can. So one of the interesting questions, if we are chemists, or maybe it's a semi-interesting question, but it's still a question in chemistry. So if we have these benzene rings, so there's the issue of aromaticity of these compounds. And we can now give some measure of aromaticity, not only for the ring, but also for all the molecules that also have some other rings or other groups hanging about. So that has not been in the database. It has been there implicitly. Our model just learned to predict the energy, and it has actually inferred a lot of chemistry, which I find quite impressive. And I think it's the first time that these scientific insights have been really obtained from a model. And now we are going, this is more like computer vision now. So change of topics, this is now cancer diagnosis. And who was asking the question about the regression, right? So here's it's about regression, and I will show you in a second. So this is a large, I mean, in cancer, you have a lot of co-authors for good reasons, because it involves significant things, not only from the machine learning perspective, but also from the medical side. So assume you're in the following situation. You have a pathological slice, it is an image, and you would like to classify it. And so we are doing this without segmentation, just classification. Regression comes in a second. So for this we make, because these pictures are amazingly large. They can be 100,000 times 100,000. So now we are classifying every little tile, as cancerous and non-cancerous. The problem that we have is that we only get one label for the whole image, because we know this is a cancer case or not. So we don't know actually these other labels. And now we have trained a model, like some kernel model or neural network, whatever, that does this. So you can read it up, the paper's online. So now we can ask the question, can we explain this? So the model only learns to classify cancer or no cancer. And now we can go backwards for a given slice that we haven't seen before, and can ask, so what is the cancerous thing? What speaks for cancer? That's the red part. And then this speaks against cancer. That's the blue parts. This is not cancerous. So in a way, we have a possibility to actually be assisting to the pathology, the gist. And these are different kind of questions that we can ask. So we can ask, about cancer, non-cancer. We can ask about tumor infiltrating lymphocytes, and so on and so forth. So this is again the cancer slice. This is the cancer and non-cancer decision, and the tumor infiltrating. This is the cancer. This is the cancer, non-cancer decision, and this is the overlay over the last picture of the pathological slice that is stained. So now we can ask, given all these molecular data, we can classify cancer, non-cancer, lymphocytes, stroma, and we can have all sorts of different predictions from these different models, but we can explain them. Of course, we can ask our MDs whether this makes sense at all, and I wouldn't be here to talk about it if it wouldn't make sense. But there's more. So you can actually also, there's some data around which is either in-house or also from given databases, where you have not only cancer, non-cancer, but you also have molecular markers. These are continuous values. For example, gene expression, somatic mutation, copy number variations. There's about 60,000 of them. So we have 60,000 learning problems in this case. Most of them are regression. Most of them we can predict. So literature tells us there's maybe 24 of these, for a single cancer type, there's maybe like 24 of these molecular markers that actually are known to do something in a certain cancer type. So, but we can try on all these 60,000, and most of the predictions are completely random. But we can also actually, for some cancer types, get 50 or even 100 rather reasonable predictions, which means that there is more than what is already known in the literature. And of course, since we have our method, we can go back and for every molecular feature, we can create these maps. And then we can put these maps from the pathological side together with a molecular side. And we can create some pictures that we would call computational fluorescence microscopy. Now, when we tried to publish this, the reviewers said, well, it's all nice and good, but. So we don't believe you, right? So they said, it's fine, you know, your cross-validation, whatnot, all these procedures are nice, but we would like to see some evidence. And then what we had to do was we actually had to take some of the slices from which were available in-house, and we made some predictions for these slices. We get the explanations, and we did a staining that is specific to the molecular end point, and compared this to our prediction. And so these are the pictures. So this is like the morphology on this side. These are different morphologies, as you can see. This is the machine learning prediction, and this is what we get from the staining. So you see that there's quite some overlap. And note that this slice and this slice is a different one, because the first slice has already been used, so we have to take the next slice. Already a lot can change. So if you don't see the similarity on this so much, then that could be also an explanation. But you can also see very nice similarity. You can do statistical testing and everything. So it means that our predictions were good to an extent that they would even be reproduced by the staining. So having been going through with all of you through some machine learning and the sciences and explanations from neuroscience, from quantum mechanics, and also to cancer, finally to get you back to computer vision, I would like to have some take-home messages, because I think that's important to, and again, you will get the slides. So, first thing, and we all of us said this many times, usually sensitivity analysis is not the question that you like to ask. It's the question that you typically ask is, what makes this scooter a scooter? Right? So then you get this answer. In the case of sensitivity analysis, you ask, what do I have to do to this pixel in order to make this a scooter, loosely speaking? And you can see from the gradient shattering that there's also a lot of noise in this. So, also, we mentioned the gradient shattering issue. So the explanations that you get for simple models do not necessarily work for the deep ones. And we've shown examples for that. So I hear some more. These are cars, and you have these gradient-based methods that make this a bit colorful, right? Which you already see that it's vulnerable to the gradient shattering. This is what the LRP extracts from this, and this is what, if you take this as a filter of the image from LRP, this is what the method looks at. Okay? So LRP doesn't have this gradient shattering issue. So also what we saw is that there's a number of different things that we can do with LRP, different applications. We can play around with text, with videos, with games, with quantum mechanics, with medical imaging. And in every time, Deep Taylor watches us, that we do something that is theoretically well motivated. So one thing that is super important to stress is LRP not only works for deep models, but also for recurrent models like LSTM, but also for good old kernel methods and graphical models and whatnot. Because you can always translate a kernel method into a neural network or into a graph, and then you're in business, because that's what LRP does. Very important, we've been annoyed in the past by people saying that LRP was gradient times input. No, it is not. So I think that it's, I think we very clearly pointed out that they're different rules, and we should use the appropriate LRP rule for our particular network. If we have a ReLU network, or if we have a conf network or whatnot. So there are prescriptions, we have written them in a paper, and please, if you use these methods, I know it's a drag, but it's good to read occasionally, right? Practically, because we don't want you to spend so much time in reading, we also have some software that tries to do things for you. Also, I mean, I think it's very important if you compare things. Back in the days, and sometimes still, people come up with a new algorithm, and then they compare with their dumbest competitor possible. I think this is not fair, and it also makes no sense. So you also don't have Usain Bolt run against your grandmother, assuming that your grandmother is not a sprinter. So the explanations can be evaluated by pixel flipping, which nicely talked about by Wojciech and also by Grégoire. I think the important thing to say is that this pixel flickering business is not reduced to neural nets. We can also apply it to other techniques. So it's beyond one particular model. So explanation helps to improve models. So as Wojciech just pointed out, just run it faster and you get better results. It's quite remarkable. But your video. But practically, what we found, and this is why we had last year a NIPS workshop and explaining ML, and now what, right? So we now have these techniques. We can understand things. We can see how the CaffeeNet and the Google's Net and VGG, how they behave, what kind of errors they make, what kind of horsing is there. All these things are available to us now. The question is, how can we get mileage from that? And there are some first, papers that are out that are using these techniques to improve the models and to gain insight. So I mean, for personally, talking in quantum mechanics, gaining insight was the now what. So, but this is wide open. I think all of us can profit if we could be using these and other methods. It's very important to find flaws in models if we use them later on in any kind of situation that matters, in the sciences, in industry. So I think that we need to understand what is happening. So getting new insights in the sciences was one of the things that I was trying to explain to you, although I left out some of the intricacies of quantum mechanics and chemistry, but it's actually quite fun because we can learn a lot of new things. So embedding in chemical compound space, embedding in atom environments, using these type of models for molecular dynamics and learning what is happening there. This is a fantastic and very open and dynamic field. Slightly interdisciplinary, as you may imagine, but I'm a theoretical physicist by training, at least in the master part, so it's fun to me. Then one thing that was already mentioned by, I think Wojciech was talking about it. All of you are probably familiar with the support vector data description or outlier anomaly detection methods. So in support vector data description or any of these other algorithms that are in this school, you try to find what is the normal mode of the data and everything and all what is left. And so we took this as an example for unsupervised learning and try to see whether we can also apply our methods for explaining to that. And so if you think about, say, for example, this image here, I don't know whether you see this nicely. So if you take an edge detector, a Sobel one, if you're familiar with these things, then this is what. So we take little patches and see what is anomalous, and then we make a visualization from this one class classification using deep Taylor decomposition. So here I don't know whether you see this, but it's an optical illusion. You have this grid, and in the middle there's a circle that is slightly tilted. You almost don't see it. So this is why the anomaly detector says something. So if you take this kind of structure, then that's what the edge detector will give you, and the anomaly detector will give you these kind of things. For example, on the parking lot, this is the most anomalous place object that we find here. This is what our one anomaly detectors says, and how we explain it. So this is like again the edge detector, and this is now some other image, and this is again this object. It's an anomaly here, whereas the edge detector wouldn't detect it. So what I'm trying to show with these slides is not only what is this? Rain in Utah. I don't believe it. Anyway, what I'm trying to show is that in any kind of unsupervised learning algorithm, we can also apply explanation. This being one. So there is all our tutorial try to convince you that explaining and interpreting nonlinear models is essential. It's also orthogonal to improving deep neural networks and other models, because we can gain some insight that can allow us then to improve the models. We need to open the black box. It's super important for the sciences, for medicine, for AI in general, because we need to know whether our models are truly intelligent or whether they're just cheaty intelligent. We have a theory with this, and the final thing, I said this already, please think about Usain Bolt, right? And who you would like to compete with. So this is now the final slide. Thank you very much for your attention. There's the tutorials will be online. There's software, there's online demos, there's some papers out there. We have spent a lot of time writing papers which are actually published in journals. People don't do this nowadays, but I'm a big fan of it. I would like to ask questions.
From all your presentation, I saw the input is all single images. Have you tried this method on multiple input network, or like multitask training, which is multiple output? if we want to directly apply your GitHub code to a multiple input network, what kind of things should we pay attention to? Is there anything we need to make some adaptation of that?
I mean, all of this, as also pointed out by Wojciech, with this MNIST example. So this is it's multi-class. It's inherently multi-class. You can ask, is this a 3 and why is it a 3? Because it has been classified a 3. But maybe the 3 is 0.8 and the 9 is 0.2, right? So you can ask, why is this a 3 and not a 9, or why is this a 9 and not a 3, and you can all ask these kind of questions. Yes.
I'm not asking the multi-classification problem. I'm asking if I have one single output,
yes,
but I have multiple image as input, that
yes,
to give that one single output, say it's a regression problem.
Okay.
For that case, yeah.
Yeah, in the case of a regression problem, you can apply the same thing. So I mean, it's basically these molecular markers, they were continuous numbers.
Yeah.
So here you would have a regression to these continuous markers, and then you propagate this back. So I mean, there's no difference in why having multiple images is different than in this medical imaging case.
Okay, that's fine. Thank you.
Okay, at least from the principle.
Hello, very nice talk. I did have a question. You talk about relevance. At a certain point, you say that you can only say if this pixel, how much it contributes to that particular class.
Yes.
But at a certain point, you also say that you can say negative pixels that contribute to not being that class.
Yes.
How can you take that?
Well,
because what makes a dog is not the negative of what not makes a cat, let's say.
Okay.
So
that's the cats and dogs question. I didn't show any cat pictures. I should have. But practically, it depends very much on which rule we take. So there was the epsilon rule that Wojciech was talking about that has positive and negative aspects. In this kind of question, you would take that one, and then you could get the furry, fluffy details of a cat is different, and maybe then there's the dog's tail or the long ears would be, something that would come out. Maybe we can find some slides in our.
Yeah, but assuming that you have a multi-class, let's say 10,
yes,
like your digits, you have 10 digits, right?
Yes.
You can say what makes a free. So
yes,
giving an image of a free, what makes a free. But you cannot say what does not make a free, right?
No,
because
you can.
You cannot just sum the relevance of the other ones and
No, you can, because you can ask this question for every little class as compared to the other classes. Yes, exactly. Yes. So exactly, this is your. I'm not looking at slides, yeah. So okay, so you see here the differences. I mean the difference. So you see mostly red, but there's also some blue. So which says, basically there's, there should be nothing on top, right? And if you now, look at, I don't have the slide here, but you can look at it afterwards.
Yeah, but what is that blue? What that blue means in that particular image?
Oh, so I think what Wojciech showed was much nicer. It was the 3, right, and the 9, okay?
Yeah.
And so you would see that, for the 9 there was a reason why this was a 9 and not a 3, because you can ask, given this image, you can not only ask, what is the reason for it being a 9, but also you can ask what is the reason for it to be a 3, right? And then the 3 would put some blue in the spot where the circle is closed. So which, no?
I'm still not convinced, because you can.
I mean, it's not a matter of convincing. It's a matter of finding.
What can make the image of a 9 being a 3, but you cannot say the inverse of that.
No, it's not true. So I mean, I can show you this. I mean, I would have to find it. I'm not sure whether I can find it.
That's fine. We can discuss later.
Yes, but maybe I can find it. I'm not sure. Here, this is the image. Okay? So, you classify this as a 3, but there's also 9 other classes. And then you can ask, what is the relevance for this being a 9? Of course, it has not been classified a 9, but you can also take the relevance that the model gives in the forward path and propagate this backwards, and this is what you get. So you see that basically, this part is missing for the 9. This is what the model says. This part is good because that also 9 has it. This part is also good, and so this part in a 9 is usually more round.
Yep. Okay. Fine. Okay. I don't get how that blue can be taken from that image, because you ask it. So you're asking there if it is a 9, right?
Yes.
And then you're inverting the value.
No, we're not reverting anything. We are using the standard LRP rule, in this case epsilon, I think, and then we are getting these different colors. We're not reverting anything.
But your colors are only positive. You cannot get blues and reds at the same image.
This was the alpha beta rule. So there are different rules. So they're different. This is something that all of us said several times. So I think that if you ask a certain question, you should use the right rule. So Wojciech, do you want to add something?
No, I mean, what Grégoire is right, within the Taylor framework, it makes the assumption that the relevance is a positive. Right? But this LRP framework is more general. So you have alpha beta rules, the epsilon rule, and the Taylor interpretation is a special case is the alpha beta rule. For alpha equals 1, that equals 0. And for that, if you apply this Taylor technique for that, you have just positive relevance.
Okay, thank you.
More questions?
You want to have one more question after the?
You can.
Okay. So regarding your medical classification of cancer, you mentioned something like you can now you have like 50 good predictions where they only had 20 relationships defined in the literature before,
Yes.
but thousands of basically random
Yes.
predict. How do you differentiate between the 50 good and the thousands?
So you can do statistical tests.
But do you have a truth to say? These
No, there's
50
no
are-
truth. I mean,
Okay.
you don't know the truth,
Okay.
right? I mean,
Okay. It's simply
so
random
but you can say you can ask whether you're predicting well or not.
Okay.
And in the case where you cannot predict, then this is really random, and you can make a statistical test with reshuffling or some random labels or stuff like that, so that because there's two variances. There's the limited data variance, and there's the variance that comes from maybe your model, and the variance that comes from your data.
Okay. Thanks.
Okay. Thank you for asking this question. It's a